My name is Hugo. Oliveira. I'm coming from the Free University of Bozen-Bolzano, Italy. Niloofar couldn't make this conference, and I will present in her place, okay? So the title of the work is Silicone Carbon-Based Black Field Elastomer-Based Self-Healing Strength Sensor. So in the last few years, there has been a lot of research on flexible electronics and sensors for a variety of reasons. First, because they can present high sensitivity in some situations. They can also present some low cost, also depending on the application. High strength survival. They can be, since they're flexible and conformable, they can be integrated in many different surfaces. They can be lightweight also. Many substrates can be biocompatible. And now, something that is interesting now, and especially related to the talk that we talked yesterday in panel, is self-healability. And this is very important because it can represent a cost reduction, increased lifespan, low electronic waste production. And this is really aligned to what we were talking in yesterday's panel. So in terms of increased lifespan, we can think about electronics that after they are damaged, they can be reused. And this is something very interesting in terms of the cost reduction. So flexible electronics and sensors have been used in many different applications. For example, soft robotics, healthcare monitoring, structural health monitoring, sports activities, wearable systems, automotive, aerospace engineering. And now it will be really, really good if we could develop in future some thin film transistors for bendable circuits, also substrates that can be, after they are damaged, they can self-heal. So based on this, we decided to study a self-healable substrate. And we developed here a sensor, a stretchable sensor, using the self-fusing silicone tape. You can buy this from Amazon, for example, and it's self-healing, it's waterproof, it can withstand high temperatures, flexible, stretchable, and conformable. So this kind of tape, normally it is used to applications like plumbing, things of everyday things, right? Plumbing, installation of electrical systems, and so on. So what we did here was to take the tape, and here we see a top view of the tape, and here a side view. And we, using thermal evaporation, we deposited a layer of chromium, and then we came with a layer of gold, and then we came with another layer of our self-healing tape with a hole in the middle so that we can have our piezo-resistive sensing material, which was made using carbon black coconut oil and EcoFlex. 1.4 parts of carbon black, 8 parts of coconut oil, and 8 parts of EcoFlex. So then we came with a cover to encapsulate our piezo-resistive material inside our sensor. Okay. Then here we see a picture of our sensor in a stretchable machine. So this is what we use it to characterize our equipment. And here we see one of the first results that we got. What we have here is we stretched our sensor in time, and 10, 20, 30, 40, up to 50% of stretch. We stretch it up to 50%. And we see that for each level of stretchability, everything is really well defined. And after we stretch it, we have an overshoot, which is related to the settling of the carbon particles inside the piezo-resistive structure, the piezo-resistive material. And we have here the initial resistance of 0.18 mega ohms. So this is the variation of resistance with the strain. And we see here a gauge factor, calculated the gauge factor around 34.6. And okay, we also cycled our sensor 200 times. And what we see here is a very stable behavior at 0. After it's stretched and returns, we have a very stable behavior here at 0% and a very acceptable behavior at 30% of stretch. We also made here a bending test, and we see here that when we change the angle of the sensor, we took the sensor and we started like changing the angle, but not stretching, just positioning the sensor on top of a curved structure. And we see a minimal influence of this angle, of the angles in the resistance of the material. And here we see just a second, let's see here. Yeah, it looks like we don't have a plugin here of QuickTime, but what we were trying to show here, yeah, it shows here we don't have a plugin. QuickTime not available. That's okay. We were showing here is that we can cut the sensor and then we take the parts and we join them together and they are healed. And so we did different types. I mean, we cut this and we assemble them again manually, and then we use it. We try to investigate more if we could improve this self-healing of the structure, like increasing the temperature up to 100 degrees Celsius, and also pressing the material for a few seconds, also at 100 degrees Celsius, and we didn't see any significant difference, so we kept doing manually. And see here we see the IV curve of our material, and see that before cutting the material and after cutting the material, we see that IV curve are very similar, which shows that the conductivity of material are also similar. So we also stretched our sensor, the pristine sensor, which was the sensor before being cut, and also the self-healing sensor. And what we see here is that at 50% of stretch, we have a very good response from the material. And after this point, it starts, we see a lot of noise. But the healing sensor, we got good behavior until up to 10%. And after that, we saw like a lot of noise in the result. So it means that you take your sensor, you have a damage in your sensor, you cut it, but it is still functional. So it's pretty much like your hand, right? You have your hand, you seriously injure your hand like with a cut, but you still can use that, right? And this is what we have with our sensor. Normally, people would like just throw away the sensor, but here we can keep using this, okay? And then now that we are limited to the deformation of 10%, we decided to compare the performance of both sensors, the sensor that was healed and the pristine sensor. And we see here very similar behavior for the healed sensor and the sensor that was not, after stretching up to 4 or 5%. We see here a similar curve, a similar behavior of the two sensors. And also the gauge factor, when we compare the behavior of the resistance with the strain, how the resistance changes with the strain of the sensor, we see here that assembling the healing sensor, we introduced some hysteresis in the behavior of the sensor when we load and unload the sensor. And we also try to investigate what happens if you take the sensor and you cut it, you join it again, and then you separate and join it again, separate and join it again. So what we saw was, what we see here is that first, when we do that for the first time, we can stretch the sensor up to almost 18%. And after you do it again, we can only go up to 12%. And when we increase the number of separating and healing, the maximum stretchability of your sensor decreases. But still, the behavior of the sensor is very similar. I mean, still, in terms of the resistance. So we also took the sensor and we cycled for 150 times. And we see here a very stable behavior at 4% of stretch, and also a very stable behavior of 1%, which means that the sensor, even after being cut, it can still be very useful. So, and in conclusion, we fabricated the self-healing sensor. We got a good gauge factor, which is comparable to some other gauge factors that we find in literature, 34.5 or 0.6. And the rupture strength was about 400 for the precinct sensor and 18% for the healed sensor. Thank you.